We're going to begin with one last oxidation reaction. I don't want to say whether I'm enjoying notability. So let's see where we were. We had been working on sort of synthesis, syn-dihydroxylation, right. So our third oxidation reaction is oxidation of alcohols to ketones or aldehydes. And you may be tempted to think of these as different reactions. You should not. If you understand what oxidation is, the consequences of a reaction just depend on what the starting material is and sort of fall out inevitably. So as an example, here is a primary alcohol, and here is a secondary alcohol. Here is an aldehyde. Here is a ketone. Which of these options, aldehyde or ketone, can I get from a primary alcohol? How do you know that? It's true. Count your many carbons. Name them one by one. Sorry. That song, I served a mission in McAllen, Texas, as I told you, spent some time in Spanish wards, and I love how those Spanish wards sang that song. You get to the bendiciones cuenta y verás cuántas bendiciones. It's really fun. Okay. I don't know if that's universal. It was maybe just my experience in South Texas, but it was fun. Okay, right. So you count your carbons. Oxidation means a loss of a carbon-hydrogen bond, an increase in carbon-oxygen bonds. We lose H. We lose basically one hydrogen, one hydride, and one proton. You can't make a ketone directly from a primary alcohol. You got to do a carbon-carbon bond, okay? So it's not worth memorizing that primary alcohols lead to aldehydes versus secondary alcohols lead to ketones. It's just the inevitable consequence of what oxidation is. Now, with aldehydes, you have another higher oxidation state, because once you get to the aldehyde, you still have another carbon-hydrogen bond that you can lose. When you get to the ketone, there's no further carbon-hydrogen bonds that you can lose to get to a higher oxidation state. So for primary alcohols, you've got these two possibilities, going to the aldehyde or going to the carboxylic acid, but this is sort of two oxidation steps. Oxidation step 1, oxidation step 2. Only one step needed for secondary alcohol to ketone. One sort of theme as we've been dealing with reduction reactions, if you remember with alkynes, we had two double bonds to reduce, and we wanted to know, are we going to go all the way down to the alkane, or are we going to stop at the alkene? We're going to have a similar issue with going from the primary alcohol to either the aldehyde or the carboxylic acid. There will be some reagents, or basically one class of reagents, that cannot stop at the aldehyde but go all the way to the carboxylic acid. There will be others that stop at the aldehyde. And I'm going to show you what those reagents are and why it works. But again, I encourage you not to think of all of these as three different reactions. Your life would be a lot easier if you see them as different manifestations of the same reaction. So let's start with going from the primary alcohol to the aldehyde and stopping at the aldehyde. The reagent of choice is called gonna love this. Pyridinium chlorochromate. So that's just another acronym for you to make sure you know, just because you're gonna need to recognize it and be able to use it. This is a oxidized source of chromium, chromium-6 oxidation state. And let me show you how this works. You begin by having the lone pairs on the oxygen attack the chromium. And what this step is going to resemble what you saw before for toluene sulfonyl chloride. You attack the chromium here, and the chloro group leaves to make a new oxygen chromium bond. Okay, and your text deals with what happens next in a slightly unsatisfactory way. Your text says proton transfer. I'm adding the quotes to indicate sarcasm, maybe. I mean, it is proton transfer, but they show, your text will show this happening. And I'm not entirely sure why. Or rather, your text shows you this happening before the next step happens. I'm not sure why they're showing you this at this stage. The other aspect that I don't like when you just say proton transfer is, well, proton transfers are easy, so just draw them if you're going to show a mechanism in a textbook. At least show it once. Whoops, I'm making up crazy stuff. Sorry. It's been a week and a half, and it's just been 1 week. It's been a painful week. So probably you remove the proton from the oxygen first. Probably at the next step you pick up a proton from whatever this was. It could be Cl minus. That's sort of the only thing around that's an option. It could be other things, but we won't worry about it. That gets you to this intermediate, which is called a chromate ester. Oh, you know what? Have I? What did I do wrong? Oh. Okay, I'm sorry. Is that better? Okay. Okay, I have no excuse for my apparent lack of consciousness this morning. So, my apologies. I promise to get the structures right on the exam, and if I don't, I promise not to penalize you for my silly mistakes. How's that? All right, so you get a chromate ester. I think your text wants to show you this so that what happens next makes some sense. So basically, this here, including these electrons, is now a good leaving group. And it's almost as though, and it's difficult to explain why, based on first principles, why this is a good leaving group. But think about it this way. You've got something that's chromium in its +6 oxidation state, which is a fairly high oxidation state. So it's going to have some affinity for being reduced. It's going to have some pull towards accepting electrons. in this first step, we have a pair of electrons that form a new bond between oxygen and chromium. And from that point on, it's like chromium now owns those electrons. And in fact, it's going to take them away in the next step. All right. Any questions so far? I've really muddled my way through that, and I apologize. Okay. So what happens next is basically an E2 elimination step. It's unconventional because you've never had a good leaving group attached to an oxygen before. But if you think about what's in green as a good leaving group, alpha carbon, alpha oxygen, beta carbon, you now have a proton that's beta to the leaving group, and that is a situation where you can do an elimination reaction. I haven't drawn the beta proton anti to the leaving group. Presumably it does need to be that way. There are no stereochemical issues to pay attention to here, though, so it doesn't matter. So I will show some base. Again, your text may show you Cl- doing that. It doesn't need to be a very strong base at all. Removing this proton, electrons kick down to make a new oxygen carbon pi bond. And then these electrons that were in the bond between oxygen and chromium leave with the chromium, and that's the oxidation step. Those electrons used to be here on the oxygen, then they were in the oxygen-chromium bond, and now they're going to leave with chromium, and that gives you your aldehyde product. The chromium leaving group is probably Cr something something minus overall. I don't know how to do formal charge on chromium, doesn't matter, and I'm not ever going to draw this again in this class, so take a good look because it's gone. But that was the leaving group. And there's your aldehyde product. So conceptually, you're making a new bond between oxygen and something that's electron deficient, and then you're taking a proton taking away a proton adjacent to that oxygen, so that the electrons in that oxygen-chromium bond actually go away with the chromium. So this is an example of a reaction mechanism that is consistent with what you expected from Gen Chem about what oxidation really is. It's the loss of electrons, right? Okay, anything you want to ask about that? Yes?
Pyridinium is not involved in the mechanism?
Pyridinium is a lovely counter ion, not involved, at least. So you could ask the question, why did they choose that instead of something else? And the answer is, I don't know. It might have to do with organic solubility. This reaction is good. I mean, it's run typically under anhydrous organic solvent. Anhydrous conditions means no water. That's actually critical because the absence of water actually is what is going to save us from going from the aldehyde onward to the carboxylic acid. You don't have to keep track of that detail. Typically the solvent that's used with pyridinium chlorochromate is dichloromethane, CH2Cl2 or DCM. That's a detail you may encounter in the text. I am going to assume, though, that when you use PCC in a synthesis, you mean that you are using it, when you use pyridinium chlorochromate in a synthesis, you are using it under these conditions so as to stop at the aldehyde. By the way, we hate long names sometimes, so instead of pyridinium, which we can't spell, chlorochromate, we're going to call it PCC, right? Anything you want to ask about that? So what are aldehydes good for? You'll get to that in 352, but you can do lots of fun stuff with aldehydes. Okay. So let's deal with how we might go on to a carboxylic acid from the aldehyde. I told you that it was the absence of water that made the big deal for the primary alcohol being able to stop at the aldehyde oxidation state. So I'm going to show you, there are 3 different reaction conditions your text presents for this reaction. That's overkill. I'm going to show you one, and we're going to leave it at that. The other ones we will forget. This is probably the most common of those 3. It's called the Jones oxidation. That name doesn't matter unless you go on in OChem, and you might hear that referred to again. So I don't know why I put it there. This will go all the way to the carboxylic acid. And like PCC, this involved a chromium-6 reagent. But unlike PCC, this takes place in water with acid. Okay? So water, got plenty of water around. Acid, got plenty of protons available for picking up from H3O+. CrO3 is, the Lewis structure is best drawn like this. It's chromium in its +6 oxidation state. The first step of this reaction is identical to the first step of the PCC oxidation, only rather than having, after we make the oxygen chromium bond, rather than having a leaving group leave, we're just going to break one of these chromium oxygen double bonds, or rather pi bonds. That's going to give us an intermediate that is identical to the intermediate we saw above for PCC. Could CrO3 be used if you could get it soluble in organic solvent and not have water present? But it's not, yeah. Not that I know of, anyway. So yeah, the key distinction really is that PCC is able to be dissolved readily in many organic solvents, whereas if you run the reaction in aqueous solvent under these conditions, you can't stop at the aldehyde. So you get this intermediate that's identical to what we did up here. So since I made a big deal out of it, now I'm regretting it. I want to use the proton transfer trick like your text uses to save time, but now I can't because I criticized it. For every idle word, men shall give an account in the day of judgment, right? Dang it. Right, so that gets you to the chromate ester intermediate that I showed you above. And again, you have a pair of electrons in that oxygen chromium bond that are going to leave with the chromium. The next step is also identical to what happens in the PCC oxidation of a primary alcohol. Some base, we don't care what it is, either water or perhaps the conjugate base of sulfuric acid, removes the proton that is beta to the leaving group, and those electrons leave. So far, there's nothing new here, right? The thing that leaves is exactly the same as it was up there. So what's the difference? And the difference is the water. So what I'm going to show you now is something that you'll talk about again in 352. But I want you to think of it in terms of by analogy, I want you to think of it like this. Suppose this was a CH2 group instead of an oxygen, and suppose you brought a strong acid in the presence of this double thank you pi bond. What's going to happen? This is chapter 10, alkene hydration, pi bond picks up the proton. Who gets the proton and who gets the positive charge? The more substituted carbon gets the positive charge, right? So you're used to the idea that you can add a proton to a molecule that has a pi bond, and you're going to put the proton on the thing that's less substituted so that the more substituted thing can have the positive charge. Now, compare what we're showing here with this aldehyde. Let's compare and see what the differences are. We have this aldehyde in water. What is the HOMO of the aldehyde? Lone pairs, no longer the pi bond, right? Because lone pairs are not involved in bonds. But can lone pairs remove protons? Sure, that's just acid-base chemistry. We've done that tons of times, right? So we're going to remove a proton from, oops. Oh, why does it do that? There it is. Going to remove a proton from H3O plus to generate the oxonium ion version of the aldehyde. But I'm going to draw a resonance structure in which I show the positive charge on the carbon. Notice how this sort of resembles something that you've done before. Okay? So we protonate the aldehyde, and that makes the carbonyl carbon more reactive because it basically puts a positive charge on it. In the same way that if you protonate the pi bond, that leads you to a reactive intermediate that's positively charged. Am I losing you? What do you think about that? Are you okay with that? You disturbed? Go ahead.
So where does the double bond go in the resonance structure?
Onto the oxygen. So here's, oh, well, that's kind of bad geometry. One lone pair on the oxygen, now there's two. You can get from one resonance structure to the other by doing that. Yep. Okay, others? No? So now, with alkene hydration, all you did was have the, man, what's going on today? Have water attack the positively charged carbon to make a new carbon-oxygen bond. We're going to do that similarly with our aldehyde. We're going to make a new carbon-oxygen bond. It turns out, though, that you can draw what I just drew below from the other resonance structure as well. What appears to be going on is non-bonding lone pairs on the oxygen are attacking the pi star of the aldehyde, breaking the pi bond. I see, okay. And actually, either of these is valid. They're just resonance structure options of each other. They're both right. So when that happens, we'll get an intermediate that looks like this. Now there's two oxygens bonded to the same carbon. And then it's reasonable because we have lots of water present for that proton to be removed to give us this intermediate, which is called an aldehyde hydrate. It's called an aldehyde hydrate because if you look at what happened relative to the aldehyde, we added water to the aldehyde. All right? So that's the aldehyde hydrate. And the thing about the aldehyde hydrate is it results in OH groups that have lone pairs that can then attack chromium again for another round of oxidation. So this isn't as pretty as I might like to have drawn it. But what questions do you have so far? You're going to get tons of experience in 352 doing things like this where you have a nucleophile attacking a carbonyl compound. Just remember, nucleophile attacks pi star, pi bond breaks. And that's like 3 or 4 chapters in 352 that are all basically the same thing. They work on that principle. Okay, so now you have the aldehyde hydrate. You've got an analogous situation as you had before. Lone pair electrons on an oxygen going to attack chromium. A question you might ask is, why can't we just stop at the aldehyde? Why can't we just add one equivalent of CrO3 and just stop there? The answer is, I'm not sure, but some reagents, the idea is if your product is as reactive or more reactive than your starting material, as soon as you form some product, that product is going to start competing with the starting material for more of that reagent. And so that's a highly inefficient situation. In any case, we're going to assume that you have enough chromium present to do the second oxidation step. And it's going to follow exactly the same pattern that we showed you above, only it's going to be on the aldehyde hydrate instead. So here's that positive, here's this sort of neutral intermediate that has a positively charged oxonium ion here, negatively charged oxygen on the chromate. I'm going to embrace my hypocrisy. Proton transfer twice. C above. That will get us to the chromate ester intermediate that we talked about before. That will give us the good leaving group with the electrons in this bond between oxygen and chromium poised to leave. We now have, again, alpha oxygen, beta carbon. We have a beta proton. We can do the E2 style elimination reaction, remove the proton, make a pi bond, electrons leave with chromium, and that gets you the carboxylic acid. All right? Yeah. So it's basically 2 rounds of the same thing. The same principles apply, same kinds of mechanistic steps. Go ahead.
So how are there all of these bases and acids existing in the same solution?
Okay, well, how are all these bases and acids existing in the same solution? Let's talk about what we have at any given time because of these, this reactive material. We've got H3O plus, which can be an acid. We've got H2O, which could be a base. We also have HSO4 minus by sulfate anion that could be a base. You also have, along the way, intermediates that have negatively charged oxygens, and maybe this oxygen is the base for another molecule's reaction. And so because we have so many options, you're going to be generic about it.
Some of them are going to exist around the other ones.
Yes. Yep. Right. Some of them are going to exist around the other ones at the right times. Good. Okay. Yes?
Yeah, for that conversion of primary alcohol to aldehyde, like the first step, in the study guide mechanism, we had like H2O acting as the attacker and H3O, but we don't have those things with PCC. I was wondering, do we care what the base?
Right. So in PCC, what have we got for a base? Well, you have, it might be this group on another molecule that does this deprotonation. If you're wondering what the heck I'm talking about, I am too. But maybe this negatively charged oxygen is actually on another adjacent molecule is the one doing that. It could also be a more convenient and easier thing to draw is might be to have you have a Cl minus leaving group at that stage, which we forgot about, but it's present and it could do this. I hate that option because I know that HCl has a pK of minus like 9 and so or 7, and so Cl minus is a terrible, terrible base. But it basically doesn't matter because it works. Yeah, so you don't have water, it could be Cl minus, it could be another copy of this molecule. Yeah?
What was the name you gave for the second one you did? So this is the PCC and then the
Oh, the CrO3 in sulfuric acid, the Jones oxidation, if you want to remember that, that's easier than saying CrO3 in sulfuric acid.
there's not like another specific name though.
No. No. Yes?
Why doesn't the proton just be taken from the negative?
Great question. Why doesn't the oxygen here just reach over and take the proton? The answer to that is maybe. It may be a little bit more complicated. It has to do with bond angles. Real briefly, let me say, if you're going to break the oxygen-hydrogen bond, you've got to be dumping electrons into the oxygen-hydrogen sigma star, which is pointing out this way. So there's just a question if that sigma star is here. There's just a question, can this oxygen actually get around and reach that? And some evidence in OCHEM suggests no, but it's so tempting and convenient that some people say, I don't care, yes, and just do that, and that's okay too. I just don't like it because it's a four-membered ring and the bond angles don't work out that great. Four-membered transition state is what I mean, but okay, great. Others? Yeah.
Yeah, so with the exams, are you going to want to identify what's needed in a mechanism? Or?
So how do I test mechanisms on the exam? Sometimes I don't. I ask questions where you have to know the mechanism to get it right. Other times I will say which of these steps is correct or incorrect. So let's talk about ways in which I might botch a mechanism and try to tempt you into choosing something that was not okay. Is that all right if I do that? All right. So let's just take this example of going from the primary alcohol all the way to the carboxylic acid. You see the correct mechanistic steps here. Trying to think about what I might do. Oh, sure. So one sort of really bogus option might be this. It gets you to what you want, only H minus is a leaving group, really? pKa of H minus is of its conjugate acid is 35. You want to have that thing leave in water without immediately making hydrogen gas and starting an explosion. So no. So that's one example. Another thing I see sometimes is people, and I will. Is people use arrows for protons and not electrons. So an example of that might be, let's go to the stage where we needed to protonate the aldehyde, right? A less effective or bad example would have been something like this. I know what you mean by that. The proton goes on the oxygen, but you're not following the rules for communicating things, so it's wrong. Arrows are about electrons, right? Not about movement of nuclei. So you have to show lone pair electrons on the oxygen removing a proton from hydronium and not the hydrogen moving. Okay, so that's an example of things that people do wrong. So there would be, for example, that would have been like B, C, D, F, K, and then you choose the one that's right. Yeah. Okay. A couple of things. Why can't we do another reaction to oxidize that carboxylic acid further? There's no more hydrogens to pull off, exactly. You could presumably, such things exist, you could presumably protonate the carboxylic acid and then attack the protonated species with water again to give you this kind of intermediate or species. That's known, it's not particularly stable. and you could even imagine one of these attacking chromium, but there's no beta proton to remove. So you're done, you stop there. Another question might be, if I'm using a secondary alcohol, I stop with the ketone, why can't I go to the carboxylic acid from the ketone? Same reason, you can make the ketone hydrate in water, but there's no, but there's no beta protons to be removed once we would add the chromium to the oxygen. So for the aldehyde, it does not matter if you use the PCC reaction or the Jones oxidation reaction conditions. Either one works. There's no other option than to go to the secondary alcohol, and there you stay. For the primary alcohol, if you want to stop at the aldehyde, you need to use PCC. If you want to go all the way up to the carboxylic acid, you need to use the Jones oxidation. And if for some reason you first decided you wanted to stop at the aldehyde and then you change your mind and want to go all the way to the carboxylic acid, that'd be highly inefficient, but you could use the Jones oxidation conditions to convert the aldehyde into the carboxylic acid. Incidentally, ethanol oxidation is something that at least at other institutions goes on frequently inside students. And it actually becomes important to oxidize ethanol all the way up to the carboxylic acid, because aldehydes are not great things to have around biologically. They can start to interfere with a lot of things. All right. Anything else you want to know there? So I kind of feel like it might be a good time to tell you a little bit about how biology does oxidation, because it's an entirely different strategy. Notice that with these two reactions, our goal was first to get these two electrons on the oxygen bonded to a metal that could take them away, and then we did a proton, and then we removed the beta proton to get the aldehyde. In nature, and maybe you remember just a couple of minutes ago I told you about the less effective example of maybe having hydride leave. That's actually not too far off from what biology does. So we'll just call this biological oxidation, and I'm going to introduce a reagent that you're going to ask, should you memorize it? And I'm going to say, don't bother, but you'll see it again and again in your future, so you ought to be aware of it. NAD+, or nicotinamide adenine dinucleotide. If you want to know how to spell it, look it up. It's a version of a nucleotide, but it has a base that you probably haven't seen before. Okay, so now I'm going to draw all of the rest of the nucleotide part. Really probably shouldn't, but dang it. Ribose. Yep. Still going. This is the adenine part. And now we have to see if I can remember the structure of adenine, or whether I'm a hypocrite in that way too. That's pretty close. All right, nicotinamide adenine dinucleotide. This portion is nicotinamide, and it needs a positive formal charge on the nitrogen. Here's the dinucleotide, here's the adenine portion. The nicotinamide portion is the business end of the molecule, so simplify where possible. Okay, that's NAD plus. The plus comes from the positive charge on the nitrogen, which I forgot again, right? So how is this an oxidizing agent? This portion of the molecule, the nicotinamide portion, is a hydride acceptor or a hydride receptacle. It is waiting and willing to react with H minus. And you can tell that's the case because you can draw a resonance structure of this molecule in which you have a positive charge on the carbon that is opposite the nitrogen. You see maybe how I got from the resonance structure on the left to the one on the right? So in a lot of ways, NAD plus is like a carbocation. Not completely, because it's a resonance stabilized carbocation, but you've got this carbon that's electron deficient. So if your liver alcohol dehydrogenase and you're encountering lots of ethanol in the blood of some poor sap who, that is ethanol, right? We don't want to make the poor sap blind with methanol. So what happens with liver alcohol dehydrogenase is the enzyme holds the alcohol very, very close to the NAD plus, especially to the positively charged carbon. And what happens, I'm erasing stuff because I need to draw it better. What happens is a side chain in the liver enzyme will remove this proton. At the same time, electrons will kick down. It's almost as though we're going backwards, right? Now the oxygen is at the beta position, this hydrogen is at the alpha position, and perish the thought, hydrogen is the leaving group. H minus is the leaving group, but it doesn't actually ever exist as H minus because it's directly handed off to NAD plus. In fact, if you were to look at the transition state for this reaction, you would see that H minus is basically never existing. It's just directly handed off from one to the other. But we'll show that process happening but you have to envision it as a direct handoff and not as a H minus is floating around for 20 minutes until it finds the NAD plus. So contrast that with what we did above with the chromate ester, and you can see sort of the interesting differences. With the chromate ester, we remove this proton and those electrons leave. With the NAD plus oxidation, we remove the proton from the alcohol, and then the hydrogen here is the thing that gets transferred. When it gets transferred, the product is the reduced form of NAD plus, and this is called actually NADH. This is used all over in biology, but you can actually take this hydrogen and its two electrons and deliver those to the electron transport chain in mitochondria and drive ATP synthesis in addition to a bunch of other stuff. Okay, so biological oxidation, a lot of ways to do it. There you go. Questions? Yes?
So why don't we synthesize like that?
Why don't we synthesize like this? Could you do this in the lab? Yes. You can buy liver alcohol dehydrogenase. You can buy NAD+. They're probably more expensive than some of the chromium reagents, so yeah. There's also the issue of substrate specificity. Enzymes evolve to bind specific molecules, whereas organic chemists want flexibility to do a lot of different structures. Okay. Sorry we had to slog through that Friday. I hope you have a good weekend and get some rest. I'll see you on Monday.